If you don't know who this man is, his name is Bryan Johnson. He's a tech multi-millionaire who started Braintree, which acquired Venmo and then was acquired by PayPal for $800 million, and he made off like a bandit. And now he's devoted his life to a prolonged N=1 experiment where he's trying to reverse aging, or maybe more accurately achieve aging escape velocity. I'll speak a little bit more about Bryan and my opinions on him at the end of this video, but he did go viral for this one stunt where he was taking blood donations from his 17-year-old son and then giving blood donations himself to his older father. The results of that experiment were kind of interesting. Bryan abandoned it in the past, but I predict he might pick it up again in the future, and I'm gonna tell you why again at the end of this video. But anyway, when I first saw this headline about Bryan taking blood from his son, I thought to myself, like everybody on the internet, wow, this guy is a lunatic. And quite honestly, the article that I saw was behind a paywall, so I didn't end up reading it until recently. But now I'm gonna eat a slice of humble pie because I just read a paper that came out in Nature Aging that blew my mind and that Bryan Johnson is gonna love. Stick around, you're gonna love it too.
Welcome to my channel. Stay curious.
The paper I want to cover is entitled Small Extracellular Vesicles from Young Plasma Reverse Age-Related Functional Declines by Improving Mitochondrial Energy Metabolism. And it describes how these little packages in your blood, small extracellular vesicles, or sEVs for short, can transfer metabolic youth. Isn't that exciting? Now, let's not waste time and dig straight into the data. They started their experiments by looking at the chronic effects of transfer of young mice sEVs from young mice, 2 months old, to old mice. What are the long-term chronic effects? And the first obvious question is there an impact on longevity? And the answer is absolutely, without a doubt. Here are the survival curves. And what you see in red is the survival curve for the older mice given the young sEV injections weekly. And what you see is a 12.4% improvement in median survival. 34.4 months in the mice getting the young sEV injections versus 30.6 months in mice getting the PBS control injections. PBS just being the control. The details of that aren't super important. Now, another question is, well, was health span improved? And again, the answer is a shocking yes, or a consistent yes. You can see that just phenotypically in the mice. The mice getting the sEV injections from the young mice just have a glossier coat. They look healthier and younger. And they actually did an objective analysis called a frailty index, which is kind of looking more at biological age versus chronological age. And what you're looking at here in figure C is the frailty index for the young mice in blue. So blue is young mice throughout the paper. And then the older mice with the control injection in white. And then the red is the older mice with the young sEV injection. And what you can see is the frailty index for the older mice given the young sEVs comes back down to a level that's similar to the young mice in blue. And I'm really emphasizing the colors because this is the color scheme they carry throughout the paper, which make the data very easy to interpret. So I'm going to show you several graphs. And every time what I want you to look for, where there's the blue, white, red, is the blue is always young mice. The white is always older mice that are controls, and the red is always going to be the older mice with the sEV injections or something equivalent. So what you're going to look for is, does the red, the older mice given the young sEVs, come to approximate or come closer to the blue, which is the actual young mice, as compared to the white, which is the older control mice? Hopefully that makes sense. They also measured a ton of other parameters. For example, in male mice, looking at testosterone, sperm quality, and fertility, all of which went up dramatically. So for example, for fertility, young males produced 8 pups per litter, whereas older males produced 4 pups per litter. But when the older males were given injection of the young sEVs, they again produced 8 pups per litter, which I think is super cool. And there were improvements in things like VO2, locomotion, how much the old mice moved around, which again returned to near young mice levels, and improvements in bone density. And now this is crazy, there were changes in the brain with injection of the young sEVs into the older mice, decreasing loss of cortical and hippocampal volume. The brain was protected from atrophy. In this study, in addition to looking for chronic benefits of young sEV treatment, they looked for acute anti-aging benefits by injecting older mice 7 times with young sEVs over just 2 weeks, and then tested for things like improvements in memory. And what they found were significant improvements in memory in things like the Morris-Water maze test and other functional tests of memory. And again, I can go through the methodological details, but really what you're looking for, as I explained before, is you have the blue, which is the young mouse, the white, which is the older mouse, and then what happens when you give the older mouse young sEVs? That's the red column. Does it approach the level of the blue, the young mouse? mouse? And yes, indeed it does. There are functional improvements in memory with acute treatment of young sEVs in older mice, showing an acute benefit in addition to a chronic benefit of these young sEVs from young mice, which is super cool. And they looked in the tissues of these mice for biomarkers of aging. So for example, one is called senescence-associated beta-galactosidase, which you can see here in blue. And basically the idea is with aging, there's going to be accumulation of this aging marker, and the anti-aging signature would be a decrease in the blue. And you see that here. It's actually very obvious. So the far left is the young mice. The middle column is the aged mice that are controls, and the right column is the aged mice that get the young sEVs. And what you're looking for is in the far right column, the old mice with treatment, do they have a decrease in blue, again, towards the young mouse phenotype? And it's very, very obvious that they do. So you can look at any row, any tissue, but spleen, for example. You see the young mice, not much blue. The aged mice, tons of blue. But then when you give aged mice the young sEVs in the far right, the blue starts to go away. And this was just one aging marker, the senescence-associated beta-galactosidase. But they looked at many other aging markers too, such as P21, P16, reactive oxygen species production, AGE generation. And basically you saw this consistent pattern whereby even acute treatment with just 2 weeks of young mouse sEV reversed aging biomarkers, in addition to improvements in functional tests in things like memory and exercise patterns. So again, they're showing there's the chronic benefit of young sEV treatment, but there's even an acute, really potent benefit of young sEV treatment, which is absolutely shocking. They then went a step further to look at the heart of metabolism, mitochondria, the powerhouse of the cell, because in large part, aging is a process of accumulating metabolic dysfunction. So it would make sense that in aging, mitochondria and their functionality is impaired, and this could potentially be reversed with sEV treatment from younger mice. What did they find? Well, figure 4 as a composite shows you the answer, and the answer is again a resounding yes. There's an anti-aging effect on mitochondria, whereby in aging, mitochondrial activity, like complex 5, ATP synthase activity goes down, ATP production goes down. Mitochondrial DNA content, yes, mitochondria have their own DNA, goes down, and mitochondrial number can also decrease. And all these things, all these features of mitochondria were reversed, were improved with young sEV treatment, which is really astounding. And here's something that is super cool. Because sEVs aren't actually that species specific, you should be able to not just take young mouse sEVs and give them to old mice, I guess that's the plural, and improve old mice health, old mice mitochondrial function. You should be able to do the same thing with young human sEVs transferred to old mice. And indeed, they show they can do that. They show they can take sEVs from human beings, give them to old mice, and recapitulate the anti-aging effect. Isn't that cool? I'll actually read that section from the paper. Behavioral tests revealed that young human sEVs efficiently ameliorated cognitive deficits and improved endurance exercise capacity in aged mice. This was supplement figure 13b. And young human sEVs also significantly accelerated ATP production from mitochondria, stimulated complex 5 ATP synthase activity, and increased mitochondrial DNA content in the hippocampus, the brains, and muscles of aged mice. Isn't that freaking awesome? But now, here's another question, one that's probably been bugging you throughout this entire video. What is the magical anti-aging substance in these little packages that are floating around in your blood? What's inside them? And what the scientist identified is the active component, or at least one of the active component, is something called microRNAs. So you may know that DNA is generally transcribed into RNA, and then RNA is generally translated into protein. But that refers to messenger RNA, which is coding RNA, meaning the RNA codes for protein. But not all RNA actually codes for protein. There are non-coding RNAs, including microRNAs, which are regulatory. They can regulate the production of other proteins, but they themselves are not turned into proteins, but they are metabolic regulators. And indeed, they found in this study that there were specific microRNA signatures of young sEVs that differentiated them from old sEVs, and that these young sEVs were the active components inside the sEVs that transferred the anti-aging effect. So you actually see that here. And one thing I really want to draw your attention to between E and F is E is mice, F is humans. And what you see is the signature, the young microRNA signature, is the same between them, where the young microRNAs, I think it's actually in red, are the same three. The same three are the anti-aging mRNAs between humans and mice, suggesting this is all pretty conserved, or consistent with the idea that it's all pretty conserved. Now, among the targets of these microRNAs was something called PGC1 alpha. PGC PGC1 alpha is the master regulator of mitochondrial biogenesis. So you can see how this puzzle is starting to fit together. And what you see is with treatment with young sEVs or treatment with these microRNAs, PGC1 alpha levels and activity were boosted. So now we have this picture whereby the young sEVs are carrying a particular cargo, these microRNAs, which are positively affecting metabolism in part through positively affecting the master regulator of mitochondrial biogenesis to improve overall metabolism and have this massive anti-aging phenotype. Now, PGC1 alpha isn't the only target and it's not the whole picture, but you can start to see how the picture starts to puzzle together. Isn't that beautiful? And it makes a lot of sense. I want you to pause for a minute and think about this, because the biological cascade, as I've explained it, as these data have shown, makes sense. But then you juxtapose it to something that on the surface sounds crazy, like a tech billionaire taking blood from a 17-year-old. And you see that headline. I saw that headline and I'm like, this is nuts. But then you have to eat your slice of humble pie when the paper comes out and it's like, wait a minute, there's biology here, there's data here, there are things that we didn't understand. I love that. I love being wrong. I love feeling like, Nick, you idiot, like, how did you not think deeper about this to begin with? That's the way I'm feeling right now. I hope you're feeling that way too. I love that feeling. Now, in closing, I actually wanted to return to Bryan Johnson and my thoughts on him. I said before, when I first saw the coverage on him, I thought he was probably a little bit cuckoo and maybe needed to find another life purpose and something to do with his hundreds of millions of dollars. I've changed my tone. I actually think, upon thinking more about it, that he and I are probably a lot alike. What he's doing, which I think is absolutely fantastic, is taking his money and doing a rigorous and public open science N=1 experiment for the benefit of the world. I love to do it. I just don't have hundreds of millions of dollars and the free time to do it on scale like he does. But in retrospect, I really admire what he's doing with his open science. And when you actually sit down and get to listen to him speak, he's a pretty rational guy. I first heard him speak in long form on Trevor Noah's podcast, which I'll link below, and it was a fantastic discussion. Him talking about just his observations on human behavior and his philosophies about health. One of the things I actually got out of the conversation is I was fully convinced that what he's doing, which is a very rigorous, probably intimidating protocol for most people, he genuinely loves it. He loves what he's doing. And it's a way for him to enjoy and engage in life, and is not actually restrictive to him, which was a mental shift for me about how different people live their lives. I also thought he was actually really funny. I thought he had a great ability to laugh at himself, which I really respect. And one other thing that we do share is we both love dark chocolate and macadamia nuts, but he keeps his calories tightly locked in apparently to 1,977, so I'm pretty sure I out-eat him in terms of macadamia nuts at least. But that aside, I thought it was a great conversation. I actually think he's a pretty interesting, open-minded, and science-forward guy. And in terms of his young blood experiment, it was quite interesting. The way he explained it was he abandoned it because he wasn't seeing clinical benefits in himself getting the transfers from his 17-year-old son. But actually, what I didn't realize upon first looking at the coverage, literally just looking at the headline, I was being pretty superficial, was the origin of that experiment actually had to do with his father, who had been a heavy drug user and had obesity and was approaching potentially the end of his life. So Bryan had offered to his father to do a plasma transfer to him to give his father benefits. And then in addition, his son volunteered, wanting to make it a, son, father, grandfather family activity with multi-generational plasma transfer, which actually, to me as a total dork, sounds really fun. Bryan didn't see benefits from his son, potentially because Bryan's biomarkers were already so tuned in and he already probably had the phenotype, at least a metabolic phenotype of a young adult. But his father had massive improvements. If I'm recalling correctly, I think it was a 25-year decrease in aging velocity rate or something like that. And you can listen to the podcast with Bryan and Trevor because he brings it up there. But bottom line, his father actually appeared to benefit. And what's more, while Bryan may not have benefited potentially because his phenotype, his metabolic profile was pretty tuned in, I hope he comes forward and gives his impression of these new data, because they were just doing plasma transfers. But now if we understand the active component, these small extracellular vesicles in the plasma that are exerting the effect, I wonder if he's going to extract and concentrate or bioengineer super anti-aging sEVs for his personal use, and then maybe there's a trickle down or a scale up effect whereby they become commercially available. I would certainly be interested, and I will donate as well if anybody wants to take from me as a subject. I like N=1 experiments. But anyway, with that, I hope you found this video really interesting. I generally think, to be perfectly honest, the anti-aging science is kind of hooey, and maybe I should change my tone on that. I do think that reading this paper really caused a cognitive shift in me, and these data I found really compelling and exciting, even if they're not all human data. I think, we have a gut reaction to some things we hear about anti-aging, and there have been some cases of anti-aging science fraud, and people look at Bryan Johnson and just kind of laugh at him. But I think having an open mind about these kind of things and acknowledging that, we laugh at some human strongly held notions from 50 years ago, to be humble and think, in 50 years, what are we going to laugh about? In 100 years, what are we going to laugh about? Weirdly enough, reading papers like this do help me acquire that philosophical perspective. I thought you found this interesting. I really love this video. Sorry, I love this paper. I hope you love this video, and I hope you have a good day.